You know how to build recursive functions for sequences, but those aren't as useful as just a regular function. So that's what we're going to practice now. Let's consider the function that's in front of you. First, let's ask the question, what kind of function is it? Is it arithmetic, geometric, or other? To see if it's an arithmetic function, of course, we see if there's a common difference. So let's see what the common difference between, or the difference between the first two terms is. So 13 minus 20 is negative 7. Okay, how about 6 minus 13? Well, that's also negative 7. How about negative 1 minus 6? It's negative 7. And of course, negative 8 minus a negative 1 is also negative 7. So we have an arithmetic sequence here. And we know that we can define an arithmetic sequence recursively by first saying what the first term is. F of 1 equals, so what's the first term? It's 20. And then we just write this statement that says, to get any next term, we take the previous term and we minus 7. So there's our recursive definition. Pretty straightforward. But it's not very useful. For instance, if we said, what's the 30th term in this sequence? We wouldn't be able to just plug in 30 anywhere. What we could do is we could say the 30th term is the 29th term minus 7, but then we'd have to go and find the 29th term, and we can't find the 29th term without finding the 28th term. And so you'd have to write out every single term to get to the 30th term, and that's not very useful. So what we're going to do now instead is we're going to figure out how to create just a regular function, not a recursive function. Okay? And what we're going to write that in the form of f of n equals something. So what we're going to want to be able to say is, let's put 30 in there and find the 30th term, or let's put 100 in there and find the 100th term. Now we just have to figure out what goes in here. So let's take a second to do that. So when we write a regular function, it sometimes helps to see the table of values here that have the inputs and the outputs for the arithmetic sequence or the geometric sequence. And what we can see is that we have negative 7 between each term, which is another way to say that every time we have a term, we have a negative 7. So we could write that we have negative 7 times the number of terms. The only thing is, we don't have negative 7 the first time. So the number of times that we add negative 7 in the sequence is the number of terms we have minus 1. Okay, so let's just review what that means. If we're here at 3, for instance, the third term, we've added negative 7 once, twice. We haven't added it 3 times. So we wouldn't want to say negative 7 times 3. We would want to say negative 7 times 3 minus 1. So that's 2, because we've only added negative 7 twice. Now, what have we added that negative 7 to? Well, the very first value, that 20. So we can add that to 20. And this is the beginning of our regular definition for the recursive function. So again, what are we saying? We're saying any term, the value of any term, is negative 7 times that number minus 1 plus that original value, which is 20. And now we can simplify this side. And we'll check this at the end to make sure that it makes sense to you. So f of n equals, let's use the distributive property, negative 7n plus 7, and then there's that plus 20. And now we can just simplify f of n equals negative 7n plus 27. Okay, now does this make sense? Well, let's test it. Let's put 1 in for n and see if we get 20 out. So negative 7 times 1 would be negative 7 plus 27 gets us 20. Let's try 2. negative 7 times 2 is negative 14 plus 27 gives us 13. So it looks like this definition is working. And again, the way that we got here was to say we have a common difference, negative 7, and that is going to be added a number of times in the sequence. And for any particular point in the sequence, it's going to be added that number of terms minus 1. And then you add your start value. And now we can answer questions like, well, what is the 30th term of the sequence? And then we just put 30 in for n. And I'll just do the math really quick. That's negative 210 plus 27. And so that is, let's see, negative 183, I believe. So what have we learned here? Well, we can take the information about an arithmetic sequence and create a function that's a lot more straightforward than our recursive function, and then we can really use that function to find the value of the sequence at any term. The other thing to notice is, look at this here. This function looks very familiar. It's just a linear function, like a linear equation. It's in mx plus b form, and so we realize that an arithmetic sequence is a lot like a linear equation. Now let's look at a geometric sequence. Here's a geometric sequence that's already in the table, and we can figure out that it's a geometric sequence by looking at the common factor. So 6 divided by negative 3 is negative 2, or in other words, we multiply negative 3 by negative 2 to get 6. And if we take negative 12 divided by 6, we also get negative 2. And 24 divided by negative 12, also negative 2. And negative 48 divided by 24, also negative 2. So these are common factors, and we know that we therefore have a geometric sequence. And we can write a recursive function for this geometric sequence like we're used to. So the first term of the geometric sequence is negative 3, and then we can say that the next term is always equal to the previous term times the common factor, negative 2. So there's our recursive function. Now, just like with arithmetic sequences, though, the recursive function is only useful to a certain degree. You can only find the next term if you know the previous term. But you can't, for instance, find the 27th term very easily, because to find the 27th term, you'd have to know the 26th term. But you don't know the 26th term until you know the 25th term, etc. So what you need to do is change this recursive function into a regular function, just like we did a moment ago with arithmetic sequences. So let's figure out how we're going to do that. So remember, what we want from a regular function is a definition that is f of n equals some expression here. And to help us figure out what that expression is, I've written out each of the functions for f of 1, f of 2, f of 3, f of 4, and f of 5 from the table here. I've done it a little bit differently, though. Let's take a look. So f of 1 equals negative 3. We can just read that from the table. Now f of 2, I could have written that f of 2 equals 6, but instead I kept the common factor in there. So I said f of 2 equals negative 3 times negative 2, because that's how we get the 6, is negative 3 times negative 2. Same with f of 3. I said it equals negative 3 times negative 2 times negative 2 again, because that's what we did here. We multiplied negative 3 times negative 2 and by negative 2 again to get to that negative 12, and etc., etc. Now I could keep going on, but my hand would start cramping from writing all of those negative 2's. So I was thinking we should write this in a simpler way. And let's first do this with the 5 one here. Gosh, we don't want to write negative 2 times itself 4 times. There's an easier way to write that. And that's negative 3 times negative 2 to the 4th power. We can use exponents. And same with this one. This is negative 3 times negative 2 to what power? That's right, the third power. And then here we have negative 3 times negative 2 to what power? The second power. And here we just have negative 3 times negative 2. We could say it's to the first power. And then actually, we could even say that this is times negative 2 to the 0 power, couldn't we? Because anything to the 0 power is 1. The reason I write that is so you can notice a pattern. Look at this number here, 4, and this number here, 5. Then this number 3 and 4. Can you see how this is the number n, and this needs to be the number n minus 1 in each case here? Even clear over here, where n is 1, well, 0 is 1 minus 1. So now we can see the pattern, and we can write our regular function. F of n equals negative 3 times negative 2 to the n minus 1. And that's how we can write a regular function for a geometric sequence. And what's really great there is then we can find, for instance, the 10th term. We just put 10 in for n. 10 minus 1 would be 9. Use a calculator to do negative 2 to the 9th power, and then multiply that by negative 3, and we get the value here. And this should also look pretty familiar to you because it's very similar to an exponential function, where you have a starting value and you multiply that by some number to a power. So exponential functions and geometric sequences are very similar. So now you know how to, with an arithmetic and a geometric sequence, write a non-recursive function that's more useful for you to explore those patterns.